Have you ever stopped to think how we know how big something is, or how heavy it is, or how much space it takes up? The answer is measurement. Measurement is the amazing science of figuring out size, amount, or degree using a standard unit, like inches, grams, liters. It's not just something we do in a science lab, it's something we do every single day. When you see how tall you've grown, that's measurement. When you help bake a cake and add 2 cups of flour, that's measurement. It's fundamental. It's basic. It's totally essential to science and life. Without it, we couldn't build bridges. We couldn't fly airplanes. We couldn't even know the right size shoes to buy. Think about it. Our world is built on measurement. Engineers need precision to build skyscrapers. Doctors need precise doses to heal people. Astronauts and their mission scientists need incredibly exact numbers to send rockets to the moon and back. Measurement turns guessing into knowing. It's a universal language for scientists, for builders, for cooks. It lets us communicate with accuracy. That's a powerful tool, wouldn't you agree? In our virtual lab adventure today, we're going to unlock the secrets of measurement: length, area, volume, and density. Let's start with the most basic measurement of all: length. Length tells us the distance between 2 points. It answers the questions: how long, how tall, how wide. To measure length, we need a special tool. The most common tools are rulers, meter sticks, measuring tapes. These tools are all marked with standard units. In the United States, we often use inches and feet. In science and most of the rest of the world, we use the metric system: centimeters, meters, kilometers. For our lab today, let's grab a ruler that has both inches and centimeters. That way, we can see how they both work. So, how do you use a ruler? It's all about being precise. First, take the object you want to measure, like a pencil. Place one end exactly at the 0 mark. Don't start at the very edge. Always find the line marked 0. Now look at the other end. Read the number that lines up with the tip. Make sure you're looking straight down, not from an angle. That's called parallax error. Imagine measuring your science textbook. Align 0 to the left corner. Read the right corner. 28 centimeters. The book is 28 centimeters long. If it falls between numbers, use the small marks. On imperial rulers, those are fractions of an inch. On metric rulers, they're millimeters. Count the little lines for accuracy. Measuring a curve? A rigid ruler won't follow it. Use a flexible tape or lay a string along the path, mark the ends, then straighten the string against your ruler. With a bit of science thinking, you can measure almost anything. Now that we've mastered length, let's move on to area. Area is a measure of how much flat surface an object covers, like the space you'd paint on a wall. Instead of simple units like centimeters, area uses square units: square centimeters, square inches. We measure length and width at the same time, a surface, not just a line. Let's start with a rectangle. A book, a door, a phone screen. To find area, measure 2 things: length and width. The formula: area equals length times width. Back to our science textbook. Length 28 centimeters, width 21 centimeters. Multiply to find area. 28 times 21 equals 588 square centimeters. But not everything's a rectangle. A circle, think cookie, think frisbee, has its own formula. Area equals pi times r squared. Don't worry. Pi is approximately 3.14. Measure the radius, square it, multiply by pi. Voila! The area of the circle. Irregular shapes, like a leaf or a puddle, use graph paper. Trace the outline, count full squares, count half or more squares, ignore less than half. Add full and half or more squares to get area in square units. Science is awesome. We've measured 1 dimension, length, and 2 dimensions, area. Now the 3rd dimension, volume. Volume is the amount of space an object takes up. A box's length and width give base area, but volume tells how much stuff fits inside all the way to the top. We use cubic units like cubic centimeters and cubic meters, or liters and milliliters for liquids. 1 cubic centimeter equals 1 milliliter. For regular solids like a rectangular box, a rectangular prism, measure length, width, and height. Volume equals length times width times height. Let's try a cereal box. Length 20 centimeters, width 8 centimeters, height 30 centimeters. Plug in. 20 times 8 times 30 equals 4,800 cubic centimeters. A cylinder's volume is the area of its circular base, pi r squared, times its height, v equals pi r squared h. A sphere's formula, volume equals 4/3 pi r cubed. measure the radius, and calculate carefully. These formulas let us find the volume of perfectly shaped objects without filling them with water. It's that easy. You're just multiplying 3 dimensions to find total space the object occupies. Calculating the volume of a perfect box is one thing, but what about a lumpy rock, a toy car, or your house key? These are irregular solids. We can't use a simple formula. Instead, we use water displacement, discovered by Archimedes when he noticed bathwater rise. Eureka! Use a graduated cylinder. Fill to a known volume, say 50 milliliters, and read at eye level from the bottom of the meniscus. Record 50 milliliters. Gently slide the object in. Don't drop it or you'll spill water and ruin the measurement. The water level rises, it's displaced. Read the new level, 75 milliliters. Subtract, 75 minus 50 equals 25 milliliters. That's the object's volume, 25 cubic centimeters. This works for anything that sinks and fits in the cylinder. Remember, 1 milliliter equals 1 cubic centimeter. You just measured the volume of a complex, irregular shape using nothing but water and a little bit of science. Section 6. Getting heavy, let's talk about mass. Before density, we need mass. You might say weight, but in science mass and weight are different. Mass is the amount of matter. It stays the same on Earth, the Moon, or in space. Weight is gravity's pull on mass. You'd weigh less on the Moon, but your mass would be identical. We measure mass with a balance or a scale. In labs, triple beam or digital. Digital is easiest. Turn on, make sure it reads 0. The units are grams and kilograms. A paperclip is about 1 gram. A large textbook is about 1 kilogram, 1,000 grams. Scales can be very precise. Let's measure our rock. Place the scale on a stable surface. Turn it on, tare to 0, and place the dry rock at the center. Wait for the reading to stabilize. Let's say it reads 65.0 grams. Record it. The mass is 65 grams. For liquids or powders, don't pour onto the scale. Put an empty container on, press tare so it returns to 0, then add the substance. The display shows only the substance's mass. It's a neat trick. Section 7. Putting it all together, the density equation. We have now learned how to measure length, area, volume, mass. We have all the pieces of the puzzle. Now we can understand density. How much mass is packed into a certain volume? High density means lots of mass in small volume. Low density means little mass in large volume. Density helps predict sink or float. The formula is simple. Density equals mass divided by volume. Use the triangle helper. M on top, D and V at the bottom. Units are grams per cubic centimeter or grams per milliliter. And they're interchangeable because 1 cubic centimeter equals 1 milliliter. Let's calculate our rock's density. Mass is 65 grams. Volume is 25 cubic centimeters. Density equals 65 divided by 25, 2.6 grams per cubic centimeter. What does it tell us? Water's density is about 1 gram per cubic centimeter. Our rock at 2.6 is greater, so it sinks, as we saw during displacement. Wood at about 0.7 is less, so it floats. Density explains why a huge steel ship can float, but a tiny steel nail sinks. Section 8. Tips from the lab. How to measure like a pro. Good science needs accurate, reliable data, and that starts with your measurements. Always double-check your work. Measure twice or 3 times. If readings differ slightly, take the average. Don't rush. Be careful and methodical. Tool tips. For rulers and cylinders, read at eye level to avoid parallax error. For digital scales, tare or 0 before use. Pay attention to units, centimeters, milliliters, grams. A number without a unit is meaningless. 5 inches or 5 miles. Big difference. Object too big for a cylinder? Use a larger container filled to the brim, set it in a bucket. Carefully submerge the object. Collect the overflow. That water equals the object's volume. Pour the overflow into a graduated cylinder to measure it. Keep neat records. Write the formula first. Show values plugged in, and state your final answer with correct units. Section 9. Consider the following. Why measurement rules? We've been on a virtual lab adventure. We measured length with rulers. We calculated the area of flat shapes. We figured out the volume of regular boxes and lumpy rocks. We combined mass and volume to find density. These might seem simple, but they're the foundation of STEM. Every discovery and invention started with careful measurement. A chef measures ingredients precisely. An artist measures proportions. A pharmacist measures tiny doses. A geologist identifies minerals by measuring density. Measuring lets you quantify the world. It teaches patience, precision, attention to detail, and problem solving, like finding the volume of a weird toy. It encourages curiosity and using tools to find answers. When you measure, you engage with the world and collect data. The first step in the scientific method, observation. Next time you see a skyscraper, airplane, or a loaf of bread, remember measurement. Measuring length, area, volume, and density is a scientific superpower. It lets you explore, understand properties, and build a foundation for lifelong learning. The world is full of things to measure. Grab your tools, keep asking questions, and continue your adventure. Measurement is everywhere, and now you know how to do it.